And lastly, we're going to be looking at energy stored in capacitors, because that's the point of a capacitor, at least in a DC circuit, is to store energy. So capacitors, as I've described before, can, like batteries, store energy. Batteries store it in a chemical process in the battery that as the chemical process moves forward, the battery discharges. And if the chemical process is reversible, you can recharge a battery. So the rechargeable batteries in your laptops or cell phones, the chemical process is reversible, nickel-cadmium process, or most likely lithium-ion battery. It's a reversible process. Whereas in a typical Duracell or Energizer or Rayovac battery you buy at the grocery store to power remote controls and things like that, those batteries are not rechargeable. So if you put that battery in a battery recharger, chances are it's going to blow up or destroy the battery in some spectacular fashion. Don't do that. So capacitors store energy not in the chemical process like in a battery, but in the electric field that establishes between the capacitor plates. Remember the capacitor plates of a parallel plate capacitor, there's positive charge on one side and negative charge on the other. So electric field lines, which originate at positive charges and terminate at negative charges, an electric field is established between the plates of a capacitor. That electric field stores energy. How much energy? Well, it depends on how much charge is stored, right? If there's no charge on the plates, there are no electric field lines, therefore there's no energy. And it depends on the capacitor itself and depends on the potential across the capacitor. So the energy is given by the charge stored on the capacitor times the potential across the capacitor plates, 9 volts, 12 volts, whatever the potential difference is between the two plates of the capacitor, divided by 2. Now, typically this equation, while it is the equation for energy stored in a capacitor, typically you do not know how much charge is on a capacitor. In a circuit, you know the capacitance value of a capacitor because it's written on the capacitor. This is a 5 microfarad capacitor, or a 20 microfarad capacitor, or a 2 farad capacitor, whatever. The voltage you know because you can take a little voltmeter and test it. So you can figure out what the voltage is pretty easily. The charge, how many electrons or positive charges are on one plate of a capacitor, that's really difficult to measure. That's actually not something we can easily measure. So this isn't the most useful form of the energy equation. However, we can rewrite it because we know Q is equal to the capacitance times the voltage, right? This is the equation for a capacitor. So I can substitute. Here's Q and here's Q. So substitute C times V for Q. Right, then you get C times V over 2, or C times V squared over 2. This is probably the most useful form of the equation because it gives you the capacitance, or I shouldn't say gives you, you need the capacitance value to find the energy, but again, that's written on the capacitor. You need to know what the potential difference is across the capacitor plates, but again, that's measurable. If you have it hooked up to a 9-volt battery and it's the only circuit element, it's 9 volts between those capacitor plates. If it's in a more complex circuit, you can use a multimeter and measure what the voltage value is and divide that by 2. Don't forget to square the voltage. Or solve this for voltage, V is Q over C, plug that in here for voltage, and you get an energy equation, Q squared is equal, over 2C is equal to the energy. Now the algebra here is trivial. You should be able to, using this equation and this equation, derive these two. It's just a simple substitution. But each of these gives you the energy. Now, if you use SI units, which I strongly encourage you to do, the energy that comes out will be in SI units. The SI unit for energy is a joule. The SI unit for capacitance is the farad. And the SI unit for voltage is, or potential, is the volt. For charge, it's coulombs. So if you plug in coulombs for charge, farads for capacitance, and voltages for potential, you will get energy out in joules. You can then convert that energy to electron volts if you want to, if the question asks you to or I ask you to, because joules and electron volts are both energy units. It's like converting feet to inches, right? It's a simple conversion. Now, energy in a capacitor, the reason we use capacitors is because they can discharge their energy very, very quickly. Unlike a battery, which is limited by how fast the chemical process goes on. If you think about it, a really fast chemical process that releases energy very quickly, we have a name for that, it's called a bomb, right? That's what a bomb is. It's a C4, dynamite. It releases an incredible amount of energy very rapidly in a chemical process. Well, you don't want to use a bomb in your camera, or you don't want to have a bomb next to you to use in a defibrillator. You'd like something a little safer. So a capacitor takes the energy from a battery. The battery can slowly charge up the capacitor, and then when the capacitor is fully charged, it can quickly release that energy. There are some advantages, distinct advantages to capacitors. You still need a battery or some other source to charge them, but once they're charged, they can release their energy very quickly. Also, because it's not a chemical process, capacitors don't really wear out, right? A parallel plate capacitor is just two metal plates separated by some material. As long as you don't overcharge it and blow the capacitor, breaking down, if a spark goes from one plate to another through the dielectric material or through the air, you've ruined the capacitor. But as long as you don't overcharge it, all you're doing is adding charge and removing charge from a metal plate. You can do that as many times as you want. Batteries, even rechargeable batteries, the reversible process doesn't last forever. Any of you who've owned a laptop, you know that, right? When you first buy your laptop, I'll use my example. I have a wonderful MacBook Air. It's about 3 years old. When I first bought it, the battery lasted like 12 hours. Now the battery lasts like 6 or 7 hours. And I'm sure in 3 years, if I still have it, the battery lasts maybe 3 or 4 hours. Because that process, the reversible battery process, only has so many cycles before it works. So there's work to create what are called supercapacitors. Supercapacitors are stable capacitors that can be charged and discharged very quickly. And because capacitors can be charged and discharged very quickly, imagine their use in, for example, electric cars. Tesla superchargers, they have chemical batteries, and a supercharger, you drive your Tesla, if you have one, over, eventually in 10 years, we might all have battery-powered cars, but you drive your Tesla over the supercharging pad, and like an hour or two, it fully charges the battery. But that's like an hour or two, right? And then longer if it's not a supercharge station. If the Tesla used supercapacitors instead of batteries, you could charge your car in seconds. Imagine how cool that would be, where you would just drive over this pad, and as fast as the electricity can get to your car can store it, and then drive away using that. Problems with supercapacitors are that, again, you have to limit the voltage. Too much energy stored, the voltage is too high, right? Higher voltage will store more energy, but too high a voltage will blow the capacitor. Also for accidents. Supercapacitors are wonderful things if you don't touch them, but if a charged capacitor gets smushed together, that releases energy very quickly and can cause explosion and fires. So supercapacitors are terrible in accidents. Whereas batteries, they're not great in accidents because you can still get chemical vapor, it can cause explosions, but actually it's a lot safer than a supercapacitor. So supercapacitors, if we can find a way to make them stable and safe, would revolutionize energy storage, where instead of creating a wall of batteries to store wind and water power, we could create a wall of supercapacitors that would allow us to very quickly charge and discharge stored energy. And with the move to renewables, which aren't always in-demand sources of energy, right? Solar energy only works when the sun is out. Wind energy only works when the wind is blowing. Unlike coal or natural gas, where you can just light it up and burn it whenever you want to get energy, renewable sources of energy, especially again solar and wind, are periodic. So when you have a lot of solar energy, you need to store it somehow. You store it in these batteries or these supercapacitors. So that ends the discussion of the electric field and capacitors. We're going to continue to talk about circuit elements moving forward in the next chapter. I'll see you there.